Hi guys, and welcome to the last video in the series on solids and their properties. This video is going to be all about covalent network solids, which is section 12.7 in your book. So covalent network solids are atoms that are covalently bonded over extensive distances in two-dimensional or three-dimensional networks. Covalent network solids have regular patterns of atoms, but they're only formed from nonmetals. So if you're looking at covalent network solids that are composed of elements, that would be carbon. So diamond and graphite are examples of covalent network solids. Compounds would be silicon dioxide, which is sand, or silicon carbide, SiC. Diamond and graphite, like I said, are probably the two most familiar covalent network solids, and usually they contain atoms from the carbon group, so carbon, silicon, or germanium, because each of these elements can make 4 covalent bonds. But in all cases, the bonding between the atoms is either completely covalent or it's more covalent than ionic. And the reason that I say that is because if you look at the periodic table, silicon is a metalloid. So metalloids could act as either one, but in the case of covalent network solids, it will be more covalent than ionic. So some properties of covalent network solids. They have very high melting points, and that's because they have strong covalent bonds. And because the covalent bonds are much stronger than the intermolecular forces, these solids tend to be much harder and have the higher melting and boiling points. The three-dimensional covalent networks are rigid and hard because of the covalent bonds at the fixed angles. This interconnected network of bonds explains why diamond is so hard and has such a high melting point. So diamond's melting point is actually 3,550 degrees Celsius. Diamond has a very, very high melting point, but it's not ionic. But the reason that it's so much higher than a lot of ionic compounds is because of this extensive network of covalent bonds. The two most common covalently networked solids are the two allotropes of carbon. So an allotrope means that even though it's the same element, it has a different form or a different structure. And these two allotropes are diamond and graphite. And so in diamond, each of the carbon atoms is bonded to 4 other carbon atoms, and so it forms a tetrahedron. In graphite, the carbon atoms actually bond in layers or in sheets, and each of the layers that you can see in this picture are attracted through dispersion forces. So the reason that diamond is so much stronger is because it is all covalent bonds. So every single carbon atom is covalently bonded, where in graphite, you could pick up a piece of the graphite lead and break it, because even though the layers are covalently bonded, each of the layers are held together by dispersion forces. So they still have high melting points because of the covalent bonds, but graphite tends to be softer because the layers can easily separate. The big difference in the physical properties of graphite and diamond, even though they're both pure carbon, they actually are due to the differences in the three-dimensional structure, so having three-dimensional versus two-dimensional. The most important application of covalent network solids are semiconductors. So metals conduct electricity very well. However, there are a lot of solids that only somewhat conduct electricity, but nowhere near that of metals. These are your semiconductors. A semiconductor is a solid substance that has a conductivity somewhere between that of an insulator, which means it doesn't conduct at all, and that of a metal. Maybe it conducts because of an impurity, or maybe it conducts because of a temperature difference. The two most common semiconductors are silicon and germanium, and they're both immediately below carbon on the periodic table. And that's because they all have 4 valence electrons. So the group 4A elements tend to be the best semiconductors because they have 4 valence electrons, so they will form single covalent bonds with 4 neighbors, similar to that of diamond. Semiconductors can actually be classified in 2 different ways. You can have an elemental semiconductor, or you can have a compound semiconductor. The elemental semiconductors all come from group 4A. You could have typically silicon, germanium, sometimes tin. The compound semiconductors are those like germanium arsenide, GaAs. With compound semiconductors, the most important thing is that they have an average of 4 valence electrons per atom in the entire compound. So if you look at germanium arsenide, germanium has 3, arsenic has 5, but if you find the average, that's 4 valence electrons per atom. With elemental semiconductors, as you move down a group, the element actually becomes more metallic. So as you would move down group 4A, notice that tin is at the bottom and tin is a metal. So as you move down, it does get more metallic, so even though tin is in group 4, that's actually a metal and not a non-metal semiconductor. With semiconductors, there is something that is called doping that we're going to look at. First, with semiconductors, the conductivity of a semiconductor is influenced by the presence of small impurities in the atoms. So the process of adding these small impurities is called doping. So think about doping as adding or injecting a small amount of impurity to something. Now, doping actually changes the conductivity by adding an element with more or less valence electrons. You can have 2 types of semiconductors. You can have N-type and you can have P-type. To create an N-type semiconductor, you would actually add a similar element, but it would have 1 extra valence electron. So if we're focusing on silicon this whole time, if you want to make an N-type semiconductor, you would add an atom with 5 valence electrons, like phosphorus. Phosphorus would be similar enough that it would fit into the lattice of silicon, but now the semiconductor has more valence electrons, so it has a mobile charge, a mobile electron that would move around. Now this says that it carries negative charges throughout. This does not mean that the semiconductor is negatively charged. This just means that the negative charge is what moves through the semiconductor and what allows it to conduct electricity. The second type of semiconductor that you can have is called a P-type semiconductor. In a P-type semiconductor, there would now be holes in the lattice. So with the P-type semiconductor, you would add a dopant that has 1 less valence electron. So if we're focusing on silicon, that has 4. Let's say we add boron, that has 3 valence electrons. There's 1 less valence electron. Now, it's not positively charged. It carries the positive charge throughout. The hole in the semiconductor, the hole in the lattice, is actually what moves throughout the semiconductor. So now these holes, which are referred to as positive holes, move through the semiconductor, and that is actually what allows the charge to move. Now, the N and P-type semiconductors actually help control electron flow, and this is what is used in modern electronics. So devices that are made of semiconductors, or more specifically silicon semiconductors, are really essential components of most electronic circuits. So computers, cell phones, those all contain semiconductors that allows charge to flow. In your notes, there's a QR code and there's a link to YouTube. I highly recommend that you watch that. It's a Veritasium video, if you're familiar with that YouTube channel. He is a great speaker and he's just great at explaining a variety of things. So I highly suggest that you take a look at that Veritasium video. It's about 5 minutes, maybe close to 6 minutes. But he actually shows you semiconductors and he dresses up like a silicon semiconductor. So watch that, take any notes to that, and then work on the book problems for chapter 12.